Okay, so today we will be starting with the lecture 2 of some basic components of concepts of chemistry, and today we will be studying about the separation of components of a mixture. So like I was talking in the previous lecture, that matter is classified into two broader categories, which is mixture and pure substances. Now pure substances are compounds and elements which actually cannot be, the constituents of pure substances cannot be separated. But for mixture, we can actually separate the components of the mixture depending on what type of the mixture it is, or it also depends on a few factors which I have listed out. Now the separation depends upon the physical state of the substance, whether the substance present is in solid, liquid or gaseous state. So this is one very important criteria. Then we should also know the physical properties. So what are the physical properties? Like melting point, boiling point, solubility are its physical properties. So let's say suppose we have two substances A and B. So we should know their solubility in solvents, in various different solvents. Let's say we know that B is soluble in some solvent S in which A is not soluble. So we can separate by solubility. Or if both of them are soluble in some component S, we should and we know that let's say B is more soluble in solvent S than A, then also there is a different method for that. So physical properties is also important. So knowing these is important about the mixture that we are separating. Then it depends upon the choice of method that is used. Now what does it depend upon? Like how do we decide the choice of method? It depends upon the type of mixture to be separated. Now what can be the type of mixture? It can be a solid-solid mixture, a solid-liquid mixture, a solid gas mixture, liquid-liquid mixture, liquid gas mixture, and a gas-gas mixture. So we will see how these examples using various different techniques. So for now, understand that there are 6 different types of mixtures that we have to separate. Then the second factor on which the choice depends upon is the nature of the component to be separated. So the compound that we have to separate is a solid or a liquid or a gas. It depends on so it also depends upon the nature. Okay, so there are, as I've listed down, there are 12 different techniques that are actually used. So one by one we'll be discussing each technique, and then we will understand how does it work. So we will also maybe applying to some examples and then actually understanding that how does this work, and this will help us in various experiments that are being carried out in chemistry labs, and theoretically also it is very important. Okay, so first we'll start with filtration. So the first that we are taking is filtration. Now when is filtration done? When we have an insoluble solid present in a liquid, then the best technique is filtration. Okay, so this is a picture of a filtration. So we have a liquid and an insoluble solvent, and we have that in a filter paper, right? So what we will do is we will filter that out using a filter paper and a funnel, and what we will get is a filtered solid. Now this filtered solid is separated from the liquid. Now this is the liquid and this is the filtered solid. So what is the condition for filtration? That the substance should be insoluble. So it is just present in the liquid and we are simply decanting it. So this is this is filtration. Now the next important technique is crystallization. What do we do in crystallization is a crystalline substance is a substance which is soluble, or it is miscible in a it is present in a solution. So we can remove the substance by crystallizing it, okay, from the substance. Now what is the example of crystallization? So for crystallization, what do we use? For what can we use? For example, copper sulfate crystals are present in an aqueous solution, so crystallization can be used, right? So a very, very important technique. So there are 2 ways in using crystallization. So one of this which is shown is evaporative crystallization. So what do we do in evaporative crystallization is, so we have a solution and we heat the solution, and what we do is we try to evaporate all the all the solvent from the solution, and what happens when the solvent is evaporated, the crystals are left after the solvent evaporation, and the crystals are then dried under a UV, or let's say UV light or sunlight, and then the dried crystals are ready for characterization. Okay. The other method that we can use is, rather than evaporating the complete complete solvent, what we can do is we can just heat the mixture, and then by heating the mixture, what happens, the solubility of the solute increases. So solubility is directly proportional to temperature. Okay, so if solubility is directly proportional to temperature, more is the temperature, more would be the solubility of the substance. So if it is soluble, then what will happen is the insoluble impurities will be present in the substance. So what we can do is we can then use the process of filtration. So what we were doing is we were actually decanting the solution in filtration. The insoluble solid is our impurities. We can use a filter paper and we can get a copper sulfate solution present inside. Okay. So coming back to crystallization. So what can we do in crystallization is, so we have increased the temperature, we have filtered the solution, and now here we have a solution, hot solution. Now what we'll do is we'll try to gradually decrease the temperature, and as the temperature decreases, we will find that we can get crystals in the solution itself. And once we get the crystals, now the crystals act as insoluble solid in a liquid. So that can also be done by that can also be done again, separated by a second process, second round of filtration, where now the insoluble solid is the crystalline substance that we are actually separating, and we'll get the crystals here, and we'll get the solvent back as filtrate. Okay, so we'll get the crystals, and then that crystals can be again dried, and that can be used for characterization, right? So this is how crystallization works. Now the third important method is fractional crystallization, a very important method that is used especially in the petroleum industry. Okay, so what do we do in fractional crystallization? Now if two solids that differ in solubility, so there is not just one solid, there are two solids that differ in solubility in a solvent, can be separated by fractional crystallization. Okay, actually this is not used in petroleum industry, sorry, fractional distillation is used in petroleum industry. For now we are talking about fractional crystallization. So we have two solids. Now for example, if we have, let's say, KCl and KClO3 present in water, right? So what we know is KCl is more soluble in water than KClO3. So using the differences in solubilities, we can use the method of fractional crystallization. Also, the substances that are present can be separated as crystals. So therefore, we are using fractional crystallization, right? Okay. So what do we do in this? I'll show you a picture of fractional crystallization first. So this is a picture of fractional crystallization, just the above part. Now we have two substances, so let's say desired compound and a soluble impurity. Now let's say a soluble impurity whose solubility is more is KCl in this case. So KCl, let's say, is our impurity, so it is soluble, and a desired compound is insoluble, let's say that is KClO3. Okay. Now there are soluble impurity, which is KCl, and compound KClO3, both are present. Now we will add that common solvent, which is water. We'll add water. And what we do is we heat this mixture. Now the both KCl and KClO3 will get dissolved in water. And what will we do is we'll gradually cool the mixture. So after cooling, what we'll get, the substance which is not soluble or which is less soluble will first crystallize. So in this case, what will crystallize first? KClO3. So KClO3 will get crystallized, and what will remain in the solution is KCl, since its solubility is higher. Then what we can do is, now we have an insoluble solid present in a liquid, so we can filter that out using a suction filtration. In suction filtration is similar to a filtration, except that we use a vacuum here, and we are trying to create a vacuum which increases the speed of filtration. So we get the desired compound and the soluble impurity, that is KCl, and water is present inside. Now what we can do is we can then again vaporize this liquid which is water, and we can also get KCl. So we can get KCl later, and then first we can get KClO3. Okay. The third technique that we have to use is separation using fractional crystallization. Now why is fractional crystallization used? Now if suppose there are two solids which are present, and let's say the solubility is different in a common solvent. Now for example, we have KCl and KClO3. Now what we know is KClO3 is less soluble in water than KCl. So what we can use is, we can use this fractional crystallization. Also, so there are two factors that should be taken into consideration when we are using fractional crystallization. Firstly, that the solubilities for both the components should be different. Second, the substances should be crystalline in nature. So if they are crystalline in nature, then we can crystallize them and separate them out. Okay. So how do we use this fractional crystallization? So this is a picture of crystallization. Now this is one method of crystallization where we use evaporative crystallization. So there is also one more method. So what we do in evaporative crystallization is, okay, so actually since we are discussing about fractional crystallization, so let's discuss this picture. So what we'll do is, let's say our desired compound is KClO3. KClO3 is something which we want to crystallize, and the soluble impurity is KCl. KCl is soluble in water. So these are our two solids. Okay. Now what we'll do is, we'll add water into it. Now since we are adding water, what will happen is, after adding water, we'll heat the solution. So after adding water at a high temperature, the solubility would be higher for both of them. Now, as I was telling previously, solubility is directly proportional to temperature. Okay, so higher is the temperature, more will be the solubility. So at a higher temperature, both KCl and KClO3 would be soluble, right? So what will happen is, so at higher temperature they are soluble. Now what we'll do is, we'll gradually decrease the temperature. So what we are actually using a method of gradual cooling of the mixture. So at gradual cooling, what will happen is, at some point, at some temperature, KClO3 will not be miscible. So at that temperature, KClO3 will crystallize out from the solution. Okay. So KCl is still present as a miscible salt, and KClO3 will crystallize out. So as you can see, the desired compound present in black is KClO3, right? So when it is crystallized out, what we can use is, as I was telling about the first method, which is filtration, we can then filter the desired compound, which is KClO3, using suction filtration. Now suction filtration is same as filtration, only difference being we will use a vacuum pump so that the crystallization rate, the separation rate is faster. Okay, so what we have here is, we have KClO3, and in the solution we have KCl as well as water. Okay, now suppose if I also want to separate KCl, what I can do is, I can boil off the water. I can remove all of the water and then separate KCl using the crystallization method which we were using earlier. So this is the image for crystallization. So with KCl and water, we can use this evaporative crystallization. Okay, so the next method is sublimation. Okay, so what we do in sublimation is, so what do we do in sublimation is, sublimation, from the word we know, we have learned in our 8th and 9th standards, that it is direct conversion from solid to a gaseous phase. So in sublimation, we are actually trying to separate based on the sublime nature of a substance. So this is the technique used. Now let's say we have ammonium chloride in the beaker, and ammonium chloride is present with impurities, right? So we have to separate impurities in ammonium chloride. That is, we want I would say we want a pure ammonium chloride. So ammonium chloride is sublime in nature. So as we provide heat, it does not convert into liquid state, it directly converts into gaseous state. So what we'll do is, with a funnel and a cotton plug, we are ensuring that the ammonium chloride does not move out of this assembly, and we gradually heat this mixture. What will happen is ammonium chloride will form vapors, and since as the at higher heights of the funnel we don't have higher temperatures, so it can then settle as solid into the ends of the funnel, right? Now impurities are there inside the beaker, and so we can separate. Now later what we can do is we can scratch the funnel and we can remove ammonium chloride from the impurities. Okay, so this is sublimation. Now the next important technique that we will use or that we will learn is distillation. Now what do we do in distillation is a liquid from a solution of non-volatile solute. So an important condition is the solute should be non-volatile. So now here also we have a solution. Now how is a solution? So solution is such that we have a solid solute, and we have we have a solvent. Now this solid solute, what should its property be? It should be non-volatile. Now suppose if it is non-volatile, then what will happen is that can be separated by distillation. Now how can we do is in which we are actually heating and cooling the vapors. Okay, so a very important technique is used for separation of salt. On the seashores we use distillation. Now this is the assembly for distillation. How do we do it? Now this is a stand and this is a round bottom flask. Now suppose we have a salt solution in this. Now using we have to separate salt and water. So what we'll do is we will heat the water and we will condense the vapors. So the water is heated, we will get vapors. So here is a condenser. Now what is the role of the condenser? We have a cooling water which is actually there around the condenser. So if you consider this part inside the condenser, it is at a lower temperature. Now if the vapors are passing through the condenser, what will happen is the vapors will condense into liquid form. Okay, why will this happen? Because the temperature is lower. Now when the vapors are condensed back to the liquid form, what we will get back is we will get distilled water and the salt would be left behind, right? Now this process is happening at 100 degrees Celsius. So at 100 degrees Celsius a salt cannot melt, neither can boil, because your melting and boiling points are very higher. So basically it is a non-volatile salt. Okay, so this is the reason why we can use the method of distillation. Now the next method that we will understand is fractional distillation. So this is a very important method which is used for in petroleum industry. So how is fractional distillation used? So fractional distillation can be used for let's say there are components of a miscible liquid mixture, and that can be separated by this method. Now what is the method based on? It is based on the let's say the two liquids have a small difference in their boiling points. So then we can use, and a very basic or a very important example is this fractional distillation. I'm sorry. So fractional distillation is a different concept, fractional distillation is a different concept. Now we are learning fractional distillation. Okay, so this is crude oil. This is used, so separation of components of crude oil is done in petroleum industries, and fractional distillation technique is used. Now the crude oil is firstly heated such that we get vapors of all the substances present in crude oil. What is crude oil actually? Crude oil is a mixture of various components, various hydrocarbons of various hydrocarbons. So that can be various chains of various lengths, that there can be branches. Okay, so all such things can be present in a crude oil. Also there can be naphthalene benzene like rings present. So fused benzene can be present, and various other components are present in a crude oil, right? So what we do is, so this crude oil is a viscous substance. Now we first heat the crude oil at a very elevated temperature. Now if you see at the bottom, there is around greater than 350 degrees Celsius. So all the components in the crude oil form form vapors. Now what we'll do is, at different heights we can see that there are different temperatures of the fractionating column. So this is a fractionating column. At as we rise above in the height of the fractionating column, the temperatures will decrease. Now why will this happen? Because at a lower height, since it is being heated, it will be at a higher temperature, and the temperature is maintained in such a way that there is a range of temperature at different columns, right? Now all the vapors of the crude oil are passing through this fractionating column. Now let's say we have a substance, let's say we have fuel oil. Now fuel oil has a melting point. Now fuel oil is present in what condition? It is present in vapor condition. So its melting point is around 250 to 300 degrees Celsius. Now if it reaches this column, what will happen at this column? At this column it will then condense from vapor to liquid form. So it will condense to liquid form and then it will settle into this column, okay, and then we can then separate it. Similarly, we can do this for paraffin at around 180 to 220 degrees Celsius, right? So for everything we can do. Now what happens for gases? Now the gases like methane, ethane, propane are have a very lower melting points at around, let's say, minus 18 degrees Celsius. So what we can do is we can keep a temperature of around less than 25 degrees Celsius. So even at such temperatures they are still gases. So what we can do is we can use a common pipe as an outlet, and we can take off all the gases of smaller lengths, that is methane, ethane, propane, and we can form petroleum gas. Okay, so in this way there are different fractionating columns and we can get different substances at different columns. So we have gasoline, naphtha, we also have fuel oil, we have lubricating oil, and here at around 350 degrees Celsius we get bitumen. Now bitumen is used in construction of roads. So this fractional distillation is becomes a very important technique. The next technique that we are using is steam distillation. Now what do we do in steam distillation is, we are as the name suggests, steam distillation is used and the steam as like the water vapors are used to separate some components. Now how steam distillation works? In this method, a liquid is separated from a mixture of miscible liquids. So there are miscible liquids and only one liquid can be separated from it with steam. The liquid to be separated must not be miscible with water. So the condition for steam distillation is it should not be miscible with water, right? So if this condition is satisfied, we can then separate it with steam. Now why do we need this condition? We will understand from the technique. So I will use a picture of steam distillation. So this is steam distillation. Now what we are doing is, this has a components, like a mixture of components, and I have to separate specifically one liquid out of these components. What I will do is, I will use water. So I want to create steam out of the water. So what I will do, I will heat the water. Then what will happen is, it will form vapors, and we are allowing the vapors to pass the tube to this mixture. Now what will happen is, the substance which we want to separate, that will also get heat up and that will also form vapors. So along with the steam, that substance will also form vapors and it will pass through the other tube. Now from the other tube, what we are doing is, we are using a condenser to so what will the condenser do is, the condenser will condense, which is condense both liquid which we are separating and water, so back into the liquid state. Now if they get into liquid state, now if they would be miscible, they will form one layer. Then we will have to use again a different technique to separate those two miscible liquids. But if they are not miscible, so they will form two separate layers. Now let's say the liquid which we are separating has a higher density, so it will be at the bottom of the mixture, and water has a lower density, so it will be above. In case there can also be, like, let's say there are some oils which have a lower density than water, so water would be below and that liquid or that oil would be above. Okay, so now this can be, we can just decant this and we can separate water and oil, right? So this is steam distillation. Now the next important technique, that is distillation under reduced pressure. Now this is so important that this technique is very, extensively used in organic labs. Now what do we do in distillation under reduced pressure is, so we have learned distillation previously. So in distillation we are actually trying to boil the liquid and then condense the liquid. But in in distillation under reduced pressure, what we do is we are boiling the liquid but at a lower pressure. Okay. Now why do we need this condition? Now this condition is used for substances whose decomposition temperature, so its decomposition temperature is less than its boiling point. Okay, so if a liquid has a decomposition temperature less than a boiling point, I will give you an example. Let's say the boiling point is 80 degrees Celsius and its decomposition temperature is 60 degrees Celsius. So even before reaching 80 degrees Celsius or 60 degrees Celsius, it will decompose. Decompose means what? It can, react with oxygen, or it can react with other substances. It can itself get decomposed into some other substance, and it will not remain the same substance which we are actually trying to separate, right? So for such conditions, the decomposition temperature is lower than the boiling point, we use distillation under reduced pressure. Now what we do is, now I have to reduce the boiling point of some substance. Now what I want is, I want the boiling point even less than 60 degrees Celsius, so that I don't reach this temperature of decomposition. Now what we do is, the boiling point is directly proportional to pressure. How? Now what is the definition of boiling point? Boiling point says the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. Now what I said, the vapor pressure should be equal to atmospheric pressure, and then the boiling occurs. Now if this condition is satisfied, then boiling occurs. Now let's say the external pressure, now this is a liquid, this is a closed container, here we will form the vapors, and here is the external pressure. Let's say the external pressure that we have is 1 atmosphere. So at 1 atmosphere, what will happen is, the vapor pressure that we have to form here should also be 1 atmosphere, only then the boiling will happen. Now so that happens, let's say at 80 degrees Celsius. So for 1 atmosphere, let's say we have to provide a temperature of 80 degrees Celsius, and then this will boil. Now at lower temperature, at lower pressures, what we'll do, let's say we have a temperature of 0.5 atmosphere. Okay, so at lower pressures, here we have to form a lower pressure also. Initially we were forming a 1 atmospheric vapor pressure. Now we will form a 0.5 atmospheric vapor pressure. So to form vapors from liquid to vapors, we'll have to provide a less heat. Less heat means what? A less temperature. So it will not reach 80 degrees Celsius, it will maybe reach, let's say, 55 degrees Celsius. Okay, so at 55 degrees Celsius, we can say that 0.5 atmosphere, if the external pressure is 0.5, then at 55 degrees Celsius, so the liquid will start boiling. Okay, so this condition is important, that the boiling point is directly proportional to the external pressure. So this is P external. Okay, so this is what we are doing. Now let's say our external pressure is 1 atmosphere. By some mechanism, we are actually trying to reduce the external pressure. Okay, so if the external pressure is reduced, we will reduce the temperature of boiling, and we will not reach the decomposition temperature. This is also used extensively in many organic labs, because there are many organic compounds which actually tend to decompose, and their boiling point is greater than their decomposition temperature. Okay, so we will understand the method of this distillation under reduced pressure using the picture. So this is the distillation under reduced pressure. Okay, so what we are doing is, we are having a substance. Now this is same, if you see, this is same like the distillation assembly, except that there is a vacuum pump to reduce the pressure, and there is a manometer to keep a check on the pressure. Okay, so now what we are doing is, we are heating the substance. Now by heating the substance, what happens, we will form vapors. Now at what temperature we can heat? Now since there is a vacuum, there is not a very high pressure. we have a lower pressure inside. So at a lower pressure we will have a lower temperature at which it will boil. So it is boiling at a lower temperature. So it has started boiling, and then what will happen is we have used a condenser. It will then condense back to liquid state, and then we will have the distilled liquid which is free from the impurities, or let's say other liquids. Okay. Now what happens when we use the vacuum? There can be conditions where the pressure formed is very high such that this system can go into a boom. So it can actually burst out. So to avoid this, what we use is we use a stopcock. Now what is the role of the stopcock? We actually open this stopcock and release the excess pressure, and with the help of the releasing the excess pressure, we are actually trying to like what I can say, we can release excess pressure and we can save the instrument from bursting. Okay, so this is distillation under reduced pressure, and manometer keeps a check on the pressure. So we can know if the pressure is going beyond a certain limit, we have to use the stopcock, right? And this is a condenser. Okay, so this was distillation under reduced pressure. Now the other important method is solvent extraction. Now how do we use solvent extraction? So to understand solvent extraction, first we'll understand the technique of solvent extraction. What are we actually doing is, a solid is present in a solvent. Okay, now there is one solid which is present in a solvent, so this is present in the form of a solution, right? So if a solid is present in a solvent, then what do we do? The solid is present in a solvent, then we can extract by using another immiscible liquid in which the solid is more soluble. Okay, before starting with the solvent extraction, I will tell you this distillation under reduced pressure. Now I was telling about the technique of the distillation under reduced pressure. This is the technique and this is the assembly. But actually nowadays, since this is used so extensively, so what people have done is, people have actually invented this rotary. It is same. We have a heating bath. So we have an evaporating flask where there is a mixture of liquids. Now there is a pressure inside. There is a vacuum pump inside which will try to reduce the pressure. This is the condenser and this is the receiving flask. Okay, and we have a digital control. Now what we'll do is, we will immerse this into the heating bath. We will heat the substance, and since it is it is kept at a reduced pressure, it will form vapors, and the vapors will rise into the condenser. Now in the condenser there is cool water that is flowing. Then what it will happen is, we will then have the liquid will then condense that, and it will fall into the receiving flask. In receiving flask, it is free from the other liquids or from the impurities. Okay, so yeah, I found this important, so I wanted to show this. Now next, which I was talking about, is solvent extraction. Now what do we do in solvent extraction is, now suppose a solid is present in a liquid. Now let's say that liquid is L1. Okay, but this solid can be separated from this liquid using another liquid L2, in which the solid is more miscible into that liquid. Okay, so and these two liquids are immiscible with each other, right? So these two liquids are immiscible with each other. Only then we can use this technique. Now how do we use the technique of solvent extraction? Now what we'll do is, so this is the image of solvent extraction. So okay, now suppose there is one solid. Let's say the solid is iodine. So this is used for separating iodine. Now let's say iodine is present in water. So a liquid one is water. Okay. Now iodine is more soluble in chloroform. Let's say that is liquid 2 than in water. So what I do, and also I know that chloroform and water are immiscible, because chloroform is an organic compound, water is an inorganic compound, and they are immiscible. To be more specific, water is a polar compound and chloroform is very less polar compound, and therefore they are immiscible. Okay, So now suppose the top, now chloroform is a high density, it will be present at the bottom. Now initially what we have is, we just have water and iodine is present in the water. Now what I'll do is I'll add chloroform into this, and I will vigorously shake this such that what happens is, all the iodine from the water is taken into chloroform. So not complete iodine can be taken into chloroform, because there is some distribution ratio. So according to the distribution ratio, the solute is distributed into both the solvents, but with the condition that it is more into the chloroform layer, right? Now chloroform layer is at the bottom. What I can do is, I can open this top cork and I can remove the chloroform. And later, once chloroform is removed, I can heat the chloroform, distill off the chloroform, and I can get iodine solid. And also I can remove the water and distill of water, so that I can get the remaining iodine. Okay, so this is a very important technique of solvent extraction. Now the other technique that is used is mechanical separation. So what are we doing in mechanical separation? In mechanical separation, the two immiscible liquids can be separated with the help of a separating funnel. Okay, so initially in filtration we had an immiscible solid and a liquid. Now in mechanical separation we have two immiscible liquids. Okay, so actually in both the cases we are in a way decanting it, right? So but then these two are liquids, in that it was a solid and a liquid. So this is used in mechanical separation. The same separating funnel which was used in solvent extraction is used in mechanical separation. So we have two immiscible liquids, like let's say water and chloroform. Here we have water and kerosene oil. Between water and kerosene oil, water has a higher density, so water is present at the bottom. But between water and chloroform, chloroform has a high density, so chloroform was present at the bottom in the previous image. Okay, so between water and kerosene oil, water is present at the bottom. Now these are two immiscible liquids. I can open the stop cork till the point till this water is completely taken out from this separating funnel. Then I can close the stopcock and keep the kerosene oil as it is, and this is how we can separate the two immiscible liquids by mechanical separation, right? Then there is magnetic separation. Now as the word says, there is a magnet which is used, right? So a magnet is used to separate a ferromagnetic substance. Ferromagnetic substance is a substance which is highly attracted to a magnet, from a substance which is diamagnetic, and diamagnetic meaning it is not attracted to the magnet. Okay, so this is a simple this is a simple image of how magnetic separation is used. So what we are doing is, in this picture we are using a magnet, and this is, let's say, iron fillings, and this is sulfur. Now sulfur is diamagnetic, so it will not be attracted to magnet, but iron being ferromagnetic, it will be highly attracted to a magnet. Now this technique is used in ores, in iron mining. Now what happens is, so in that there is a special technique of magnetic separation. So let's say this is a belt which is rolling, and this is rolling because of two wheels. So one wheel has a magnet inside it, the other wheel is just a wheel which is helping in the rolling of this belt. Okay, I will have a mixture of two substances which I am I have a mixture of two substances. I am allowing them to roll on this belt. Okay, one of the mixture from them is ferromagnetic. Okay, so I will have two receiving flasks, one here and one, let's say, is present here, right? So now the substance which is ferromagnetic, it will keep it will attract the magnet, and it will even roll down till this point. So because magnet attraction takes it to this point also, but the substance which is not ferromagnetic, which is, let's say, diamagnetic, will just fall off here at the tangential force acting on the substance. So it will simply fall off and we'll get into this receiving flask. But the substance which is ferromagnetic, we can get into this receiving flask. This is a magnetic substance, or I can say it is a ferromagnetic substance, and this is a diamagnetic substance. Okay, so this is actually the magnetic separation which is used in mining in O separation, in getting purified compound. So this method is used. Okay. So the last method that we have to understand is chromatography. Now what do we do in chromatography is, the principle of chromatography says that we have to separate based on the difference in degree to which various substances are adsorbed on the surface of an inert material called adsorbent. Okay. So there is some inert material present and that is called as adsorbent. And okay, so what happens is there is a difference in degree to which various substances are adsorbed on the surface. Okay, now difference in degree means what? Now let's say I have to separate these 4 dots, like it is yellow colored. Okay, so this is yellow colored, this is purple colored, this is pink colored, and this is orange colored. Now I have to separate these 4 substances. Now somehow I can see that this has gone. Now if the liquid was rising this way, so this has gone with the liquid to a higher degree. So this was adsorbed to a higher degree with the solvent, okay, on an inert material, and this was not very much adsorbed, so it was at a lower degree, right? Lower degree means I mean to say by degree the height, right? Now what happens is, here we have a mixture of the 4 substances. We are trying to write, we are like, now there is an inert material on this paper. This can be a paper, this can be a film, this can be a glass. Okay, so now we are immersing this paper inside the solvent. Now there is an inert material, solid material, which is present. By the method of capillary action, the solvent will rise. Okay, as the solvent rises, the solute also rises. So if a solute has higher affinity for the solvent than the inert material, so it will rise with the solvent, okay, till the point the solvent rises. So this is solvent front, so this is the point till where the solvent could rise. Now if the substance has more affinity with the inert material, then it will lie over the inert material and not go with the solvent. Okay, so I can say there is the competition between the inert material and the solvent, right? So inert material versus the solvent. Now what will happen is, let's say there are 2 substances A and B. Now if out of the 2, let's say A has more affinity for the inert material than the solvent, so what will happen? A will remain with the inert material, in the sense adsorbed on the inert material as soon as it reaches to the inert material, and it will not flow with the solvent. Let's say B has more affinity for the solvent and not for the inert material. So B, what will happen? It will flow with the solvent and it will not try to remain on the inert material. So as the solvent is flowing, the substance which I have named as B, which is yellow in this case, will flow with the solvent. Okay. So these were the 12 important techniques of separation, right? Now the next thing that we will learn is very important. Actually, I should have covered this in the previous lecture only, but then I missed that out. But then I will take it now. What I want to tell you is about atoms and molecules. Now write down the definition of atom. Now what is an atom? Atom is the smallest particle of an element that may or may not exist independently. Okay, so however, if it is the smallest particle of matter that takes part in a chemical reaction. So atom, let's say if I say hydrogen is the smallest part, or let's say oxygen. So these are individual entities. Although they may not be present as individual entities into the atmosphere. Hydrogen is not present as hydrogen nascent hydrogen atom, but hydrogen molecule. Similarly, oxygen is also present as oxygen molecule. Okay, so atom is the smallest indivisible entity. Okay, now what is molecule on the other hand? Now molecule is the smallest particle of matter. Okay, so the smallest particle of an element is atom. So for smallest particle of an element, is atom, and smallest particle of a matter is molecule. Okay, so matter is what? Matter is something which is present in the system, in the surroundings, or in the universe. So matter is actually what we see is present. Atom may or may not be present as an individual entity. Why? Because atom cannot exist as an independent entity, as I was explaining with hydrogen. Hydrogen cannot exist as nascent hydrogen. Hydrogen always exists as a molecule. Okay, so the smallest part of a matter is a molecule, but the smallest part of every element is atom. So hydrogen is an element, oxygen is an element. So smallest part of this element, hydrogen, is nascent hydrogen, and smallest part of oxygen is nascent oxygen. Okay, right. So as I gave the definition of atom. Similarly, what is molecule? Molecule is the smallest part of the matter, and yeah. So molecule of the element can be homoatomic, and for a compound it is heteroatomic. Okay. Now, as I was discussing about these two are what? Elements. So as I have told that elements are made up of two or more similar atoms. Okay, so hydrogen and hydrogen are two same or identical atoms from which they are forming hydrogen molecule. So this is an element, this is also an element. Okay, so molecule can now, as I am saying from the definition, molecule of an element is homoatomic. Okay, so if it is a molecule of an element, it is homoatomic. But then molecule can also exist of any as I was saying, compound. Okay, so if it is present of a compound, it is heteroatomic. Heteroatomic, the word itself says that there are two different atoms. Hetero is different, homo is same. Okay, so heteroatomic is two different atoms. Now let's say if I have water. Now water is made up of hydrogen and oxygen, where there are two molecules, or I will say two atoms of hydrogen, one atom of oxygen. So there are two different atoms present to form this compound, and this molecule is heteroatomic. Okay, so molecule can be of element, molecule can be of compound. Okay, so these were also the examples, right? So this is the basic difference between atom. Atom is the smallest part of an element, molecule is the smallest part of a matter, and whatever number of atoms are present in a homoatomic molecule is the atomicity of the element.